multiplex. In this problem, the logic realized by the circuit shown in the figure is. So we have to find what is the function of this multiplexer is implemented. Okay. So, uh, so a multiplexer is nothing but which has many inputs and only one output. Okay. So now, uh, so the Boolean function for a multiplexer can be written as we know f is equal to. Okay. So it's a three variable function, and here these are the two selection lines, and it's a 4:1 mux with four inputs and one output. Four inputs and one output with the two selection lines. Okay. So these are the two selection lines here are A and B. Okay. And C is the input. So here the output F can be written as, okay, F can be written as A dash B dash into A naught. Okay, so the Boolean function for F for a 4:1 multiplexer can be written like this. Okay, so F is equal to A dash B dash into I naught plus A dash B into I1 plus A B dash into I2 plus AB into I3. Okay, so this is a Boolean function for a 4:1 mux. Okay, general expression. Here, here we have to look what are the inputs. Okay, so here we'll write the corresponding inputs for the I0, I1, I2, and I3. So these are the selections A dash, B dash, and I0. I0 here is C. I0 here is nothing but it is C. Okay, plus A dash B into what is I1? I1 here is that is also is equal to C. Okay, next plus A B dash into what is I2? I2 here is nothing but it is C dash. I2 here is nothing but it is C dash. Okay, plus AB into I3 is also equal to C dash. Okay. Okay. So now this can be further written as A dash B dash C plus A dash BC plus A B dash C dash plus A B C dash. Fine. So now we'll take some terms common. Here A dash C, A dash and C is common in both. So I'm going to take A dash C in this common, and the remaining terms is B dash plus B. Similarly, in the next two product terms, A and C dash is common. A and C dash is common. So the remaining term is B dash plus B. Okay. So B plus B dash is equal to 1. Okay. So this is nothing but this is equal to 1. So which can be further written as A dash C plus A C dash, which is equal to, or which can be further written as A XOR C. A XOR C. So this is your final answer. So A XOR C, which matches with this option. Okay, so this is your option B is your correct answer. Okay, we'll move to the next question. So the minimum number of 2:1 multiplexers required to realize, okay, required to realize an 4:1 multiplexer. Okay. So now, let's see. So now, if you take an 2:1 multiplexer, we take an we take a 2:1 multiplexer. It has two inputs, one output, and one source. Okay. So the two inputs will be I0 and I1. And I1. With output Y and a selection line. Okay. So this is an general structure of an 2:1 multiplexer. Okay. So now here when S is equal to 0, okay, when S is equal to 0, so what happens? I0 is selected. I0 is selected. Similarly, when S is equal to 1, I1 is selected. Okay. So this is your function of 2:1. So I'll represent this in a function table as for a better understanding. S is your selection line and Y is your output. So when S is equal to 0, your Y is equal to I0. And when S is equal to 1, your Y is equal to I1. Okay. So now our job is to draw an 4:1 mux using a 2:1 mux. Okay. So now we'll see the general structure of an 4:1 multiplexer. Okay. Well, structure of an 4:1 multiplexer. So for an 4:1 mux. Okay. So here this is the input and this is the output. We have 4 input lines and 1 output line. So this is your I0, this is your I1, your I2, and your I. So how many selection lines you will have? So normally a multiplexer has 2 power n is to 1. Okay, this is your input and this is your output. And n will be the number of selection lines. N will be the number of selection lines. So now Or so how many selection lanes will have? So this is 2 power n. So 2 power 2 is to 1. Okay. So the number of selection line is 2. Okay. So that's not and that's one. So this is your MSB. Okay. So this is your general structure. So now I want to implement this 4:1 multiplexer using 2:1 max. Fine. So based on the input combination present at the selected line, okay, the corresponding input line is selected and it is connected to the output. So this is the function of the multiplexer. So now we'll implement 4:1 using 2:1 multiplexer. Okay, now I'll draw this. Okay. Now first I'll take an 2:1 mark. 2:1 mark. So it has this is the two inputs. So there are two inputs, one output, and one selection. Similarly, okay. So here I'm taking another 2:1 mark. Again, it has two inputs, one selection line. So I'll put it here. Okay. I'll put it here. One selection line and one output. Okay. So now, so for the first one mark, it has four inputs. Okay. So four inputs, I'm going to connect like this. I'm going to take like this one. Yes. I'm going to connect this as I naught, this one as I1, and the input of the second mark is I2, and this as I3. So now you have got four inputs. Okay. And now you need one output and two selections. Okay. So now here we have one selection line for this first mask and one selection line for the second mask. Now I'm going to join both. Okay. Join both this. I'm going to take this as one of the selection line. Okay. This is I'm going to take it as S naught. Okay. So now you have two outputs. So Mux should have only one output. Okay. So I'm going to take and another okay and another 2:1 Mux. Okay, which has two inputs. 2:1, which has two inputs and one selection line and one output. So the first Mux output of the first Mux is connected here. Output of this again Mux is also connected here. Okay. This is nothing but I will put this as a why not for your understanding. Anyway. Okay. And this is your and I select this selection line. I'm going to extend it outward. I'm going to take this as S1. And finally, this the output of the third multiplexer is going to be taken as a final output Y. Okay. So therefore, you need three 2:1 mux to implement a 4:1 mux using 2:1. Okay. So you need three 2:1 mux to implement a 4:1 multiplexer. Okay. So now we'll move to the next question. Okay. So our next question is going to be similarly. Uh, you are going to implement a Boolean function using this two multiplexer. Okay. So now the Boolean function f implemented in the figure using two input multiplexers is okay. So we have this diagram. Okay. So now we're going to find the Boolean expression for this. Okay. So now first we'll take this 2:1 marks. Okay. So now what is the output of this? First step is to find expression. Okay. So now here the fraction line is B. Okay. And I'll put this as a F naught for your understanding. So when B is equal to 0, I naught is selected. So this is your I naught. Okay. This is your I naught. And this is your I1. Okay. When 1 is selected, I1 is selected. So as we already discussed in the previous problem, the Boolean expression for a 2:1 mux can be written as okay. So F naught is equal to uh, this B dash into okay selection line. So B dash into I naught plus B into I1. Okay. So first selection line. What are the different possibilities? So only one selection line. The two possibilities are B dash and B. Okay. So if you have two selection lines, so it will be A dash, B dash, A dash, B, A, B dash, and A, B. Okay. Okay. So now B dash into what is your I naught value? So your I naught value here is C plus B into what is your I1 value? Here it is C dash. Here it is C dash. So this can be written as B dash C plus B C dash plus B C dash. Okay. So let me keep as it is. We'll move to the second. We'll move to the second one. Okay. So now, similarly, here can be represented as a truth table. E is your selection line here. Okay. This is selection line here. And your output here is F. Okay. So when E equal to 0, so this is your I naught, right? This is your I naught and this is your I1. When E equal to 0, your I naught is going to get selected. When E equal to 1, your I1 is getting selected. Okay, fine. So now the expression, Boolean expression for the second multiplexer, this F can be written as selection line. We have only one, so I will write this as E dash into A naught plus E into I1. So here, let me keep as it is. We'll write the input values E dash into I naught value. What is the I naught value here? It is 0 plus E into your I1 value. I1 value here is going to be A. So what is the value of E? Okay, what's the value of E? E is nothing but F naught value. Okay, so what is this? This is nothing but F. I told F naught, which is nothing but okay, F naught, which is nothing but E, value of E. Okay, so value of E is nothing but B dash C plus B C dash. Okay, B dash C plus B C dash into A. Okay, so now we'll multiply and check what the answer, which can be further expanded as A into B dash C plus A into B C dash. Just check if any of the answer is matching. A, B dash, C, A, B. So the answer A, B dash, C plus A, B, C dash. Option A. Okay. So option A is matching. So that is your right answer. Move away. Next question. So now in the following circuit, okay, X is given by. Okay, so now you have this. Similarly, similar to the previous question, I'm going to find out what is the Boolean expression. Okay. So now the first step, we'll see your first one marks. Okay, first one marks. So the expression for this, so I'm going to write this output here is y. So your y is written as, okay, your selection line is A and B. Okay, so A dash, B dash into I naught. Okay, so this is general expression for an first one. A dash B into I1 plus A B dash into I2 plus AB into I3. Okay. So now write the corresponding input values here. So A dash B into, what is your I naught? Your I naught is going to be 0. Okay, plus A dash B into, what is your I1 value? So I1 value is going to be here 1 plus A B dash into A B dash into. So what is your I2 value? I2 value is also, it is 1. And last one plus AB into, what is your I3 value? It's going to be 0. Is 0. So now this 0 goes, this goes. So therefore, which is nothing but is equal to A dash B plus AB dash. So this is the expression for the first one mux. So this I'm going to further write it as A XOR B. Okay. So we'll keep. Now I'm going to write then similarly a Boolean expression for the second one mux. Okay. This output here is nothing but X. So X is equal to, so what is your selection lines here? The selection line is going to be here Y. So this Y is going to come here. Okay. Y and C. So I'm going to write it as Y dash C dash into I naught plus Y dash C into I1 plus Y C dash into I2 plus YC into I3. Okay. So now write the corresponding input values in the next step. So Y dash C dash into I naught. So I write this value later. Y dash C into I1 value. Y C dash into I2 value plus YC into I3 value. So this is I0 value. I0 value is going to be 0 here. I1 value is 1. I2 value is also 1. I3 value is 0. So what happens? This is 0 and this is going to be 0. So it is nothing but equal to y dash c plus y c dash. Okay. Okay. So now a dash c plus y 0. Okay. Fine. So now we'll write the value of y dash. What is the value of y here? A XOR B, A y value. A XOR B, the whole dash into C plus value of y is A XOR B into C dash. Okay. Next step. This is equal to. So okay. So we see here A XOR B whole dash. So this almost resembles to an formula or is of the form x dash y plus x y dash is equal to x or y. So if you see, this is your x term. This is x dash y plus x y dash. So this is of the form. Okay, I can understand. This x and this is y. So here this y dash, here this x dash. Got it. So this can be further written as A XOR B XOR C. Okay. Okay. So or else we can expand this expression here. Can expand this expression here. Okay. Uh, A XOR B can be written as A dash B dash plus A B into C plus A dash B plus A B dash into C dash. Okay, equal to okay. So this multiply A dash B dash C plus A B C plus A dash B C dash plus A B dash C dash. So this should be the final answer. So just check your answer with the given option. So A dash B dash C, A B C, A dash B C dash, and A B dash C dash. So option A is your correct answer. Okay, correct? Okay. Now we'll move to the next question. Okay. So now, so for the circuit shown in the figure, okay, circuit shown in the following figure, I naught to I3 are the inputs to N4 is to 1 mux. Okay, where R is your MSB and S are the, there is R and S are the control inputs and Z is your output, which can be represented by, okay, can be represented by. So similarly, like with the previous problem, we will solve this. First, we will write the central expression for the 4 is to 1 mux. So here your output is equal to Z. Z is equal to uh, Z is equal to R dash S dash R dash S dash into I naught plus R dash S into I1 plus R S dash into okay, I2 plus R S into I2. Got it? Okay. So now we are going to write the corresponding values of the inputs here. So R dash S dash into what is the value of I naught? I naught value is P plus Q dash. P plus Q dash plus R dash S. Or this here I1 value here. It is only P plus R into S dash. I2 value. P, this is indicated. P into Q. P into S. Q plus R S into what's the I3 value? I3 value is here it is P. Okay. So now we are going to just multiply. So in order P R dash S dash plus Q dash R dash S dash plus okay. So this is P, right? I1 value is I1 value is P. So which is written as P R dash S plus P into Q into R S dash plus P R S. Okay. So this is the Boolean expression. So now value is not matching, so we have to further solve. The problem is not yet over. So we have to expand this term or convert this into mechanical entropy, or else we will solve this using this K-map. We put it in K-map, so we will get the required expression. Okay, so this P, Q, R, and S. This is 0, 0, 0, 1, 1, 1, 1 0 0 0 1 1 1 and 1 0. So here what we are going to do is, so we are going to plot the ones for the for this product terms. So now, for example, we see so P into R dash S dash. So P into so P is here is nothing but these two should be P. Okay. So these two rows is P. R dash S dash. R dash S dash is nothing but these two. Okay. So this is nothing but is an fair term. Okay. So you'll have a fair. So correspondingly, the two rows and this column. Okay, so we are going to plot the one. Okay, so this is P R dash S dash. Next, Q dash R dash S dash. Q dash is nothing but this and this. So we'll be going to plot like this. Here one and already one we have here. And P into R dash here. P into P is here, these two rows. Okay. R dash yes. R dash R. Yeah, this is R dash yes. So we'll have two ones here because that is an pair. Okay. Now next PQ RS dash. PQ is nothing but this is your PQ. Okay, row PQ RS dash R into S dash. So yeah, that means only one single. Okay, fine. So next PRS. P is this two one. RS is this column. Okay, got it? So now, okay, so now we are going to plot this. Okay, a pair, we are having a quad here, and we can put a pair here to get the required expression. So, which can be further written as, for this quad it is PQ plus here this pair, okay, up down pair, that is nothing but Q dash into R dash S dash, okay, plus, and this can be written as P into Q dash S. So there should be a final expression which matches with PQ. PQ have Q dash R dash S dash. We have and P into Q dash S. P into Q dash S. So option A is your correct answer. Option A is your correct answer. Okay. Now we go to the next question. Here. Okay, so the inputs to a digital circuit shown in the figure are the external signals A, B, and C. Assume the complements of A, B, and C are not available. Okay, assume complements of A, B, and C are not available. The plus 5 volt power supply, okay, the logic 1 and the ground logic 0 are also available. Okay, so the circuit diagram is given here, and what you are supposed to find here. Write down the output function in its canonical SOP and POS form. So we have part A and part B. Implement the circuit using only 2:1 mux shown in the figure, where S is the data select line, D0 and D1 are the inputs, Y is the output. The function table is also given for the multiplex. Okay. So this question is asked in the 2002. That's 5 mark question. Okay. So first we'll find the solution for the A option, part A. Okay. So write down the output function in its canonical SOP and the POS form. Okay. So the given expression. Okay. The given expression in the question is x is equal to a dash b plus a dash b dash c. This is a given expression. So in canonical SOP form. So we're going to write down first in canonical SOP form. In canonical SOP form. Okay. In canonical SOP form. So x is equal to, convert this, we are going to insert the missing letters. Okay, so that is the main concept in converting the general expression into a canonical. So here, what is your canonical expression? So each product term should have all the variables or literals in either general form or in its complement form. So here you can see the first product term, it doesn't have all the three literals. Since this is a three variable expression, each product term should have all the three variables in either true form or in its complement form. For the first product term, you don't have all the three variables. So find out what is the missing literals here. C is here missing literal. So A dash B into C plus C dash plus A dash B dash C. So now multiply this. A dash BC plus A dash B C dash plus A dash B dash into C. So now write the corresponding minterm value. So here minterm, how do you write this? So if dash is there, it is 0. If dash is not present, it is 1. So 0, 1, 0, 0, 0, 1. So which can be written as, okay, it can be written as this minterm 1 plus 1. So this is, remember, 4 to 1. So in three variables, 4 to 1. Okay, so in this should have 1. So 2 plus 1, 3. M3 plus M2 plus M1. Okay, so this is C dash. Okay, so A dash B plus A dash B dash C dash. Okay, so this should be 0. So the final answer is summation of M 0, 2, and 3. Okay, so canonical SOP form. First write your given output function correctly. A dash B plus A dash B dash C dash, and inside the missing literals, which is C. So A dash B into C plus C dash, and A plus A dash B dash C dash. And then multiplying it, so A dash B C plus A dash B C dash plus A dash B dash C dash. And then convert that into corresponding minterms. Okay. So now, after finding or after writing the canonical SOP form, the POS will be very easy. Just write the missing, whatever the midterms are written. Okay. write the other values. So that is phi of m. Okay, the canonical POS form. Write the canonical canonical POS form. Okay, canonical POS form. We are going to write this as phi of m. So 0 is written, 1 is not written. So 1, 2 is here, 3 is here, 4, 5, 6, and 7. So 1, 4, 5, 6, 7. Okay. So this is the max terms value. So write the required expression for this. So for 1, it should be written as A plus B plus C dash. This is their sum term. For 4, it should be written as A dash plus B plus C. 5 should be written as A dash plus B plus C dash. And 6 is written as A dash B plus B dash plus C. And finally 7 is written as A dash plus B dash plus C dash. Okay. So this is your canonical POS form, and this is your canonical SOP. Okay. So canonical SOP form and canonical POS form. Okay. So now we are going to implement this given circuit using 2:1 mux. Okay, with the SS data line, that is selection line, and D0 and D1 is the input line, and the Y0 is here, Y is here output line. Okay. So now to implement the given function using 2:1 mux, to implement the given function using 2:1 mux. Okay, 2:1 mux. So we are going to take the given expression. So x is equal to A dash B plus A dash B dash and C dash, which can be further simplified into A dash taking it common. So B plus B dash C. Okay. So which can be further simplified into A dash into B plus C. So this is simplified is B plus C bar. Okay. B plus C bar. So this is simplified using absorption theorem. Using absorption theorem. What does the absorption theorem tell you? The absorption theorem is nothing but okay, A plus, or I'll put in next terms, okay, x plus y dash dash y. Okay, then as x plus y. Okay, so now based on this absorption theorem, this is simplified into, so as you can see, b, the product term, okay, is present in the next product term as its complement. B is present as b dash here. So then what you have, you just leave this term and write the other b plus b dash. Okay. Right. So now from here we'll see. Okay. So now um, we'll take this first b plus c dash. We take this and implement here. B plus c dash. Okay. So b plus c dash. So writing representing this in the truth table. B and C its output F. 0, 0, 0, 1, 1, 0, 1, 1. So this B plus C dash is represented in the truth table like this. So B plus C dash is nothing but this. So 0 and remaining are all 1. So this is a representation of B plus C dash as on the truth table. So, in terms of the min terms, okay. So from min terms, so this is your min term m naught, and min term m1, m2, and m3. Okay, there's m3. So from min terms m1 and m3, from min terms from min terms m1 and m3. Okay, so here we are saying with respect to C. Okay, you are going to see with respect to C. Okay, if C is equal to 1, okay, that is if C is equal to 1, okay, C equal to 1, for this in terms M1 and M3, okay, so in terms M1 and M3, F is equal to, what is the function of F? See here, F is 0 here, and the F is equal to 0 here. And here this 1, here also this 1. That is nothing but F is equal to B. Same, okay. F is equal to B. Okay. And similarly, if C is equal to 0, when C equal to 0, this min term M C equal to 0, this min term 0 and 2. Min term 0 and min term 2. So if you look at these two, okay, when C equal to 0, this and this. So what's happened here? 0, 1, 1, 1. So, okay, which is, you can see here, okay. So what happens is, whatever may be the condition of B here, here F is equal to 1. So that is nothing but, you can write this as is equal to 1. Okay, if C equal to 0, it is F is equal to 1. So I'm going to represent this as a truth table. Okay, as 2:1 multiplex. 2:1 marks with the selection line as one selection line which is C, and here two inputs here. So here this is your D naught and D1. When C is equal to 0, okay, so this is your I naught and I1. Okay, so this is your I naught and this is your I1. Okay, so when C is equal to 0, when C is equal to 0, F is equal to 1. So you're going to write this as 1. And similarly, when C equal to 1, here F is equal to B. So that is understood. When C equal to 1, it is nothing but I1 is selected. I1 is selected. I1 which is nothing, it should be equal to B. So this is how you will be representing this B plus C dash as a twist one. Now we have to complete this A dash also. So this expression is nothing but B plus C dash. Okay. Now into K another twist one mark. It's one selection line, two inputs, and one output. So this is your final expression X. Okay. So now, okay. So now we're going to select it. Okay. So now here your selection line is going to be A. So when A equal to 0, so here this is going to be I naught and I1. Okay. This is I naught and this is your I1. Okay. I naught and I1. So when A equals 0, I naught will be selected, which is nothing but which is connected to this F. When A equal to 1, I1 is selected, so this should be equal to 0. Okay, this should be equal to 0. So now the function x is will be equal to, okay, so A dash into, what is that? I naught. I naught is here is A dash into I naught plus A into I1 is nothing but equal to A dash into I naught is what? B plus C dash plus A into I1 is here 0. It is nothing but A dash into B plus C dash. So B plus C dash, which is nothing but is an expansion of A dash B plus A dash B dash C dash. Okay. So this is your representation of to a presentation of the given expression A dash B plus A B dash C dash with a 2:1 multiplex. Okay. So we'll continue some more problems in our next video. In this video, we will discuss some problems related to digital electronics, which were previously asked in the GATE examination. The first problem, what are the minimum number of 2:1 multiplexers required to generate a 2-input AND gate and a 2-input XOR gate? Okay. So in this problem, okay, we are going to design a 2-input AND gate using 2:1 multiplexer. Okay. So first we'll start with the truth table for AND gate. So the truth table for the AND gate is truth table for the AND gate is this A, B, and output. A, B are the inputs, and Y is the output. 0, 0, 0, 1, 1, 0, and 1, 1. So the outputs are 0, 0, 0, and 1. Okay, when all the inputs are high, the output is high. This is a truth table for the AND gate. So now with respect to this, we are going to design a 2:1 multiplexer. Okay. So now we'll take a 2:1 multiplexer. A 2:1 multiplexer has two inputs, one output, and one selection line. So as this is your I naught, again input I1, output Y, and a selection line here. Okay. So here we will take one input as selection line. Okay, we'll take out of this, we'll take one input as selection line. So now whenever A is equal to 0, okay, whenever A is equal to 0, okay, what is your output? Y is equal to what? So when A equal to 0, we'll take this two. A is equal to 0. When A is taken as 0, so now what is the condition of Y? See, so Y, if you see, Y is equal to 0. Okay, Y is equal to 0. Okay, similarly, whenever A is equal to 1, when A is equal to 1, okay, so what is your Y? It is 0 is equal to, so Y is equal to B. 0, here also it is 0. 1, here also it is 1. So Y is equal to B. So this is the condition. Okay. So now here for the selection line, I have taken A. Condition, I have taken selection line as A. So when A is equal to 0, okay, when A equal to 0, what happens? I naught is selected. So what is your I naught condition? So I naught should be, when A equal to 0, I naught, that is, this should be equal to 0. Okay. So this is equal to 0. That means this is round. Okay. So when A is equal to 1, I1 will be selected, which should be equal to B. Okay. Should be equal to C. Okay. Now, so this is what an implementation of 2:1 works for the AND gate. Got it? So now, next, we'll do the same for the XOR. So now for the XOR, truth table. Similarly, A, B, and output Y. 0, 0, 0, 1, 1, 0, and 1, 1. Okay. So now, so the truth table of XOR is 0, 1, 1, 0. Okay. So similarly, we taken 2:1. We taken 2:1. Okay. So now we'll take one of the input variable. We'll take one of the input variable constant. So now whenever A is equal to 0, what is your output? So whenever A is equal to 0, see Y is equal to B. 0, 0, here also 1, 1. So Y is equal to B. Okay. So whenever A is equal to 1, okay, whenever A is equal to 1, so what is your output condition? 1 is 0. 0 is 1. That is, the relation between Y and B is inverse. So Y is equal to B dash. Okay. So now we put this as A. Okay. So when A is equal to 0, I naught will be selected. So which will be equal to B. Okay. So now and similarly when A equal to 1, I naught will be I1 will be selected, which will be equal to B dash. Okay, so this is your twist one implementation, but you don't have in a variable b dash. So in order to implement that b dash, you need an not gate for that. Okay, so in order to implement a b dash, you need an not gate for that. Okay, so for the not gate, b I so 0 means 1, 1 means it is 0. Okay, so now we take an okay, we'll take another 2:1 multiplexer. So now we take the selection this as B. So when B is equal to 0, I naught will be selected. Okay, I naught will be selected. So now, okay, so this will be so when B is equal to 0, it should be equal to 1. Okay, when B equal to 0, Y should be equal to 1. When B equal to 1, it should be equal to 0. That means it's 1. Okay, so this is not gate. So now what happens? So this is the B dash. Okay, so now you will get B dash output. Okay, so which is connected to okay. So this is one question. So now this is the okay. So now this is your implementation of a 2:1 mux for an 2 input XOR gate, which requires two 2:1 mux. Okay, so what is the question? What are the minimum number of 2:1 mux? So now we have so now for the AND gate you need only one. Okay, so you need only one mux, 1:1 mux. Okay, and for the XOR you need two mux. So check for the answer. One and two. One and two. So A is your correct option. A is your correct option. Now we move to the next question. So now in the second question, it is given as the Boolean function realized by the logic circuit shown is. Okay. So now we are going to find what is the Boolean function realized by the given 4:1 multiplexer. Okay. So now in general we know that y output y is equal to okay. So the selection line here is A and B. Okay. So it is nothing but A dash B dash into I naught plus A dash B into I1 plus A B dash into I2 and A B into I3. So this is the general expression for an 4:1 multiplexer. Now, so we'll implement the inputs. So A dash B dash. What is the value of I naught from the given diagram? So I naught here is it is C. Okay. I naught here is C plus A dash B into A dash B into I1 value here is D. Okay. Plus A B dash into what is your I2 value? I2 value is nothing but C. Here it is C dash. So this is C dash plus AB into I3. I3 here is, so this is, here becomes C dash. Here it is D dash. So C dash into D dash. C dash into D dash. So now what are you going to do? You're just going to multiply all these terms. So we'll have A dash, B dash, C plus A dash, B, D plus A, B dash, C dash plus A, B, C dash, D dash. Okay. So now here the given answer is in terms of the midterm value. So now in order to find the midterm values, you may have to convert this given in the obtained expression into canonical SOP expression. So which will take time. So what we'll do is we'll implement this using an K-map. So now this is A, B, C, D. So 0, 0, 0, 1, 1, 1, 1, 0. Here again 0, 0, 0, 1, 1, 1, and 1, 0. Okay. So now first we'll implement for A dash B dash C. So A dash B dash. A dash B dash is this row. Okay. A dash B dash C. C means the first one, with two columns. So that means you will have an pair term like this. Okay. The first row and the C means the first variable should be 1. So 1, 1. Next, A dash B D. A dash B. A dash B is this one. D. D is second variable, these two. So here we have two ones here. Next, A dash, sorry, A B dash is A B dash C dash. A B dash. A and B dash. And C dash. C dash is this first two. Okay. C dash. So here we have two ones. And finally, AB, AB. AB means this row. C dash D dash means. So we have plotted the corresponding places of the midterm. So now what we will do is write the corresponding midterm values as the function here. So therefore, f is equal to summation of m 0, 1, 2, 3, 0, 1, 2, 3, 2, 3, 4. We don't have 5, 6, 5 and 7, 5, 7, 8 and 9, 8, 9, 10, 11, 12. So these are the corresponding midterm values. So 2, 3, 5, 7, 8, 9, and 12. So the option is D. So this is your correct option. We'll move to the next question. Okay. So So in the next question, the logic function implemented by the circuit below is. Okay, so you have to find what is the logic function implemented by this 4:1 multiplexer, where ground implies a logic 0. Okay, so this is a 4:1 multiplexer. So as we already know, the general expression for a 4:1 multiplexer, which we'll write here. So F is equal to, okay, and here the selection line is P and Q. So we'll write this as P dash Q dash into I naught plus P dash Q into I1 plus PQ dash into I2 plus PQ into I. So this is general expression for an 4:1 multiplex. So now we'll write the corresponding input values. So P dash Q dash into I naught value. So I naught value here is what? Okay. So this is 0. Okay, ground, it is 0. So here this should be 1 and here this should be 0. Okay, understood? So that is here the value is 0 plus P dash Q into I1. So I1 value here is this 1 appears here. Okay, so this is I1 value is 1 plus P Q dash. P Q dash is I2. I2 is that is also equal to 1. Finally, PQ. What is your I3 value? So I3 value is here. I3 value is connected here. That is nothing but it is 0. So what happens? 0 terms value. So now therefore your answer is P dash Q plus P Q dash. So we know this equation is of the format XR. Okay, XR. So this can be written as P XR. There's nothing but so this is equal to XR of P comma Q. That is your answer. So your correct option is D. Okay. We move to the next question. Okay. So now in this question, it's given as consider the multiplexer based logic circuit shown in the figure. So here we have a 2:1 multiplexer. Okay, 2:1 multiplexer. So which one of the following Boolean expression is realized by the circuit? Realized by the circuit. So first we will consider the first multiplex. Okay. So we'll consider this output as yes. Okay. So we'll consider this first one. So where the expression for the 2:1 multiplexer can be written as x is equal to here selection line is s1. So when s1 dash here input is 0, I not will be selected, which is nothing but w plus s1. Okay, I1 will be selected, which is nothing but W dash. So it can be further written as S1 dash into W plus S1 W dash, which is nothing but S1 XR W. So this is your output at this point. Okay. So now we'll move to the second multiplexer. The second multiplexer is output is F. Okay. F. So therefore F is equal to selection line is S2 here. So S2 dash into S2 dash into. So what is your first? So first I0 will be selected. I0 here is X. I0 here is X plus S2 into I1 here is X dash. Okay, X here it will be X dash. Okay, it is X dash. So which can be further written as 2 dash into X, 2 dash into X plus X2 into X dash. So which is same of the above XR. So S2 XR X. Okay. Where X is nothing but, so which can be written as S2 XR S1 XR double. So the correct option is D. So D is the correct option. So we'll move to the next question. So now, in the circuit shown, W and Y are the MSBs of the control input. Okay. W and Y. These are the MSBs of the control input. The output F is given by. So here you have 2 4:1 marks. So here you have to find what is your Boolean expression for the given logic diagram. Okay. So similarly, we'll solve like the previous problem. Okay. So first, I'll take the first 4:1 mark. So I'll take Q. So Q is equal to W dash. Okay. Q is equal to W dash X dash into I naught. This is general expression. Okay. Plus W dash X into I1 plus W X dash into I2 plus W X into I3. Okay. So now we'll write the corresponding input value. W dash X dash into what's the value of I naught? So I will write this in the last. X W X dash plus W X. So now we'll write the corresponding input I naught value. So I naught value here is, it is grounded, so it is 0. I1 value is VCC. VCC means it is plus, that is plus 5 volts, that is nothing but it is 1. Okay, for I2 also VCC it is 1. And I3 is grounded, so that will be 0. So what happens here? So this gets cancelled, this gets becomes 0. Okay, so therefore it is equal to w dash x plus w x dash. So we'll keep as it. We'll keep as it. So now similarly we move to the second multiplexer. Output is yes. Okay. So now your selection line here is y and z. That's okay. So y dash z dash into I naught plus y dash z into I1 plus y z dash into I2 plus y z into I3. So now we will write the corresponding input values here for the y dash z dash. What is the value of I naught here? So value of I naught here is q. Okay. Plus y dash z into I1 value is also this q plus y z dash into y z dash into I2 value. I2 value here is 0 and I3 value is also 0. It's ground. Okay. 0 here plus yz value is also 0. So what happens here? This becomes 0 and this becomes 0. Therefore, your expression is y dash z dash into. So what is the value of q here? Let's see. So we'll solve the last. No, still multiply this plus y dash z to q. So now, what is the common terms here? So y dash q is common here. Both the right terms will take y dash q. So y dash q. So nothing but we have the dash plus that. Okay. So z plus z dash is equal to 1. So which is equal to y dash into q. Okay. So now y dash into q value is w dash. Okay, take it here. Okay. W dash x plus w x dash is equal to w dash x y dash plus w x dash y dash. This should be a final answer which matches with w dash x y dash, w dash x y dash, and w x dash y dash, w x dash y dash. C is your right option. We'll move to the next question. So here in this problem, we have an 8:1 multiplex. Okay, it's very simple here. So for the 8:1 multiplexer, expression can be written as y is equal to a dash b dash c dash. Okay, 0, 0, 0. Okay, into I naught plus a dash b dash c. So I1. So this is general expression. Okay, plus a dash b c dash into I2 plus a dash into bc into I2 plus a b dash c dash into I4 plus a b dash c into I5 plus a b c dash into I6 plus a b c into I7. So this is the general expression for an 8:1 multiplexer. Okay, 8:1 multiplexer. So now we'll insert the input value. Say I naught. I naught here is 0. We'll put it here. 0. That value is 0 here. I1 value is D here. I2 value is 0. I3 value is D. I4 value is 0. I5 value is also 0. I6 is 1 and I7 is 0. Okay. So now 0 terms will lead out. This, 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 this. So now we'll write the remaining values, which is a dash b dash c into p plus a dash b c and d plus a b c dash plus a b c dash. So here see whether any terms are common. So you have only two product terms. Here you have 3. So there should be any minimization should be there. Okay. So now a dash cd. Okay. A dash cd. Here also a dash cd. So take those a dash cd common. A dash cd is taken common, which leaves b dash here and b here plus a b c dash. Therefore, so b plus b dash is equal to 1. Therefore, the final answer is a dash c d plus a b c dash. This should be the correct answer. Finally, A dash CD, A dash CD, and A B C dash. C is the correct option. Okay, so we'll move to the next question. Okay. Okay. So here, similarly, we have solved already a similar problem to this. So we'll solve this problem. So first we'll write the output expression for an 4:1 multiplexer, which can be written as F is equal to, okay, F is equal to here. The first we'll write for the first 4:1. So here selection line is U and B. So therefore, I'll take this as F1 and I'll take this as F2, or that is what F. Okay, I'll take this as F. Okay, first I'll write it for F1. Okay, so expression can be written as U dash V dash. Okay, U dash V dash into I naught plus U dash V into I1, U V dash into I2 plus UV into I3. So now we write the corresponding input value. U dash V dash into, what is the I naught value here? I naught value here is 0 plus U dash V into I1 value here is 1 plus UV dash into I2 value here is, that is also 1 plus UV into I3 value here is 0. So what happens? 0 term, this 2 becomes 0. So which leaves the expression as U dash V plus U V dash. U V dash. So now we go to the second multiple. So therefore, the final F of U comma V comma W comma X is equal to, what is the selection line? W and X. So W dash X dash into I naught. W dash X dash into I1. W dash W dash X. W X dash into I2 plus Wx into I3. Okay, so now we will insert the input values here. W dash X dash, here I naught value here is, it is F1. Plus W dash X into, what is the IN value? That is also is equal to F1. And I2, I3 both are equal to 0. So plus 0 plus 0. Okay. So therefore, the expression can be further written as W dash X dash F1 plus W dash X F1. So if any terms, check if any terms they have any common. So F W dash and F1 is common here. So we will write W dash and F1 taking common, which leaves X dash plus X. Okay. So X plus X dash is equal to 1. Okay. So therefore we which leaves W dash into F1, where F1 can be further written as W dash into U dash V plus U V dash. So therefore, your final answer is W dash U dash V plus W dash U V dash. So which matches up with, so we have this is getting here answer here. So W dash into U V dash plus U dash V. C is here. So the answer is matching with the option C. So now we'll see one more problem. See one more problem here. So similarly, consider the circuit shown in the figure. So a 2:1 mux, 2:1 muxes are shown here. So you have to find the what is the corresponding Boolean expression implemented by the circuit here. Okay. So here I'll put this as small a. Okay. So the output of the first multiplexer. So F is written as, so a selection line here is X. So X dash into I naught plus X into I1. So X dash into I naught value here is Y plus I1 value here is 0. So X dash Y you have got. F is equal to X dash Y. Okay. Moving to the second multiplexer. Is capital F. That is equal to, the selection line is Z. So Z dash into I naught plus Z into I1. Z dash into your I naught value here is F plus Z into I1 value here is F dash. F dash. So here we'll write the value of F here. So Z dash into F is X dash Y plus Z into X dash Y the whole dash with dash. Okay. So further this can be written as, so I'm multiplying here X dash Y Z dash plus Z into, so apply the divergence theorem here. So X dash becomes X into becomes plus and Y becomes Y dash. So multiply this X dash Y Z dash plus xz plus y dash z. This is your answer for the output f, which matches up with x dash y z dash x y x z y dash. So x dash y z dash plus x z plus y dash z. Your answer matches with the option B. This is your correct answer. Okay. So we'll end up our class with this problem. So we'll discuss some more problems in the